Good morning. Today we're going to talk about 13-4 differentials, which are used to evaluate uncertainty or error. Okay, so we're going to look first. I'm going to connect this to something you did last year. If you look on page 237, or you don't have to go there, I'll explain the problem. We were finding an estimation of error. So they were using, we know the formula for volume, which is 4/3 pi r cubed. Okay. And let's say you measure a ball bearing. So you've got a ball bearing, which is basically the shape of a sphere, and your radius is measured to be 0.7 inches. Okay. But there could be an error in that measurement, and that error in the measurement could be up to 0.01 of an inch. Okay, so then we're going to ask us to calculate the propagated error. Okay, estimated the propagated error in the volume V of the ball bearing. Okay, so you're measuring it to be this, and your error could be as much as this. So let's talk about propagated error. What is propagated error? So if you look up here, here's a definition. Error propagation, or propagation of uncertainty, is what happens to measurement errors when you use those uncertain measurements to calculate something else. For example, you might use velocity to calculate kinetic energy. You might use length to calculate area. In our case, we're using radius to calculate volume. Okay, there's only one variable here. So of course, we're then in our, in chapter 13.4, we're going to extend this to multiple variables. Okay, but what you do here, think about taking the derivative, dv dr, which would be 4 pi r squared. And then we kind of think about the chain rule, and this dr can come to the other side. So this dv, or this differential, is going to be our propagated error. Okay, 4 pi r squared, the dr comes over here. Okay, and we're putting in the measurement into r, and we're putting in the possible error into the dr. Okay, so our propagated error, or the differential, is going to be 4 pi times 0.7 squared times 0.01. Okay, and when you calculate that, you're going to get an error of, now they don't tell us which direction that error could be in. So it's going to be a plus or minus. You could be up or you could be down. Plus or minus 0.06158 cubic inches. Okay. Now, if they asked you for a relative error, the relative error would be your propagated error divided by your volume at your measurement. Okay, so you'd have 0.06158 divided by 4/3 pi times 0.7 cubed, and you would get some kind of a relative error. Okay, you could plug that in your calculator. Now, the actual error is your actual change in volume, which is your volume calculated at a radius of 0.7, minus your volume calculated at a measurement of 0.71. Okay, if that measurement could be off, it could be as much as 0.71, could be as little as 0.69. Okay, so your actual error, if it's up this much, would be some value. Your actual error, 0.7, minus the volume calculated at a radius of 0.69, and you could get an error there. So that's an actual error. This is something that we usually didn't even need calculus for. We're just plugging it in, and this assumes that we actually have a calculator or some way to calculate this. We don't need calculus to come up with an approximation. Okay, so let's go to our current chapter, which is 13.4. Okay, and what we're going to do here, we're going to look at a couple of examples. First of all, I'm going to talk about a function where you have, let's say you have z as a function of x and y. and you're calculating the differential, the dz. So dz is going to be equal to, okay, first you find the derivative with respect to x, dz dx times your dx plus dz dy times your dy. Okay, now these are actual partial derivatives. And in this case, there is a distinction here. Because if you think about the chain rule, if you think about these dx's canceling, you'd get dz equals dz plus, and the dy's would cancel, you get another dz. So a lot of times students say, well, why do I get dz equals 2 dz's? Okay, and the reason is this. These aren't the same dz's. These are partial derivatives. This here represents your error or your uncertainty caused by the change in x. So this is the error caused by dx. This is your error caused by dy. And this is your total error caused by the uncertainty from your measurement in x plus your uncertainty from the measure in y. Okay, so let's look at an example. We're going to do example 1. We'll just do A. Here we don't even have numbers in example 1. They're just asking you to find the total differential. So for A, you've got z equals 2x sine y minus 3x squared y squared. So to find the total differential dz, you're going to do partial dz dx times your dx plus your partial dz dy times your dy. Okay, so your dz, your total differential, or your propagated error would be dz dx, so that's going to be 2 sine y, okay, and then minus 6xy squared. Okay, they don't give us a number, so we leave that dx in here. And then plus, we need dz dy, so the y derivative, which is going to be 2x cosine y, minus the y derivative of this, 6x squared y, and that's times your differential dy. This would be your answer. That's your total differential of this function. Okay. Now let's do a kind of more interesting example. We'll go to example number 3. Okay, example number 3 is on page 906. Okay, so they give us a function, z equals square root of 4 minus x squared minus y squared, and we're finding the differential dz, okay, as, and they say as, so find dz as xy moves from 1 comma 1 to 1.01 comma 0.97. So what is our propagated error or our estimated error based on some kind of uncertainty in our x input and some kind of uncertainty in our y input? Okay, so we have to calculate the differential. Actually, let's find the actual error first. So the actual error, again, actual error is your change in z, okay, from this point to this point. We're not using calculus for actual error. We're simply going to find the value of z, so calculated at one of these points and subtract from the other one, okay? So we would find your function z calculated at 1.01 comma 0.97 minus your z or your f, whatever you, this is at f of xy, z calculated at 1 comma 1, okay? And then you could plug those in and you get an error of 0.0141. That's your actual error, your actual change if you plug both of these into your function, okay? That's how far off you are when these inputs change. Now we're going to find the propagated error or the estimated error. Okay, so we wouldn't need to plug these into a calculator. We're going to use calculus to approximate things. So dz is going to be dz dx times your dx plus dz dy times your dy. Okay, I'm going to rewrite this as 4 minus x squared minus y squared to the 1/2. Okay, so your dz equals the derivative with respect to x. That's going to be 1/2 4 minus x squared minus y squared to the negative 1/2 times negative 2x times your dx plus dz dy. So it's going to be 1/2 4 minus x squared minus y squared to the negative 1/2 times negative 2y times your dy. Okay, let's simplify. dz is going to equal this 2 and this 2 cancel, so you get negative x over square root of 4 minus x squared minus y squared times your dx. Well, our change in x is 0.01, positive 0.01. Okay, and then over here, the 2's cancel. We get negative y over square root of 4 minus x squared minus y squared times your change in y. Change in y goes down by 0.03, so negative 0.03. Okay, and now we're going to plug in our values into our function. Okay, so into the x and y's here in our function, we plug in these values. So that goes in there, that goes in there, this y goes in there, and same here. And then those changes, the dx and the dy, we could say our dx was 0.01, our dy is negative 0.03. Those go in for dx and dy. Okay, so our dz is going to equal, we get negative 1 on top, 4 minus 1 squared minus 1 squared, we get a rad 2, 0.01. And then we get plus, here we get a negative 1 over 4 minus 1, so rad 2 times negative 0.03. Okay, and that comes out to be negative 0.007071 plus 0.021213. And your dz differential comes out to be about 0.0137. Okay, so that was your estimated error. This right here was your actual error, not too far off. Okay, now let's do one more example. We'll go to example 4. And this is on page 907. So example 4. Now here we have a volume of a box. So volume is equal to length times width times height. Or your x times your y times your z. Okay. And here's what your box looks like. If you look at this question, it looks like the x is 50, the y is 20, and the z is 15. And it says that, and those are in centimeters. So read the units carefully. This book likes to trick you with units. But then the error in calculating each of the sides of the box, so your dx, your dy, and your dz are all 0.1 millimeters. Okay, so 0.1 millimeters is 0.01 centimeters. So I'm going to change that to centimeters. All right. Okay, so your x, y, z. So you start with x equals 50, y equals 20, and z equals 15. But your dx, your error in measurement is plus or minus 0.01 centimeters. These are all centimeters. So it was 0.1 millimeters, so 0.01 centimeters. dy and dz are also plus or minus 0.01 centimeters, plus or minus 0.01 centimeters. Okay, so your dv, in this one, they're asking you for the propagated error and the relative error. So the propagated error is your differential, is dv. Okay, so you need dv dx plus dv dy plus dv, dz, dz. Notice we've got three parts because we've got three different inputs, okay? So there's going to be three different errors in our inputs that will all contribute to the total propagated error, okay? So your dv, the total differential, your derivative with respect to x is yz times your dx, then plus the derivative with respect to y is xz times your dy, plus the derivative with respect to z is xy times your dz. So your dv equals, and we're going to plug in these values into our function. So we're finding the error when they were measured at this. All our differentials for our inputs are over here. Okay, so the yz is going to be 20 times 15 times your dx, so we'll say plus or minus 0.01, plus your xz, so 50 times 15 times your dy, plus or minus 0.01, and then plus xy, so 50 times 20 times your dz, which is plus or minus 0.01. Okay, now these are plus and minus, but you don't want them going in different directions. For this one, unlike the last problem, we knew which direction. We knew we were off by a certain amount in the x. We knew our x was measured too big at 0.1 and our y was measured too small at 0.03. But for this one, we don't know which direction. So in order to find worst case scenario or the biggest possible error, we have to make these all in the same direction. So I'm going to make them all positive. So my dv is going to be equal to 20 times 15 times 0.01 plus 50 times 15 times 0.01 plus 50 times 20 times 0.01. Okay. And what that comes out to be is dv comes out to be 20.5 centimeters cubed. Okay. So that's our propagated error. Propagated error, or our differential. Okay. Now the relative error is equal to your dv over your v. So the dv, which we just calculated, 20.5, and divided by our volume, which would have been measured or at our measured values. So x times y times z is our volume. So we get 20.5 divided by 50 times 20 times 15. Okay, and that comes out to be 0.001367, or as a percentage, we'd say 0.1367%. Okay, so our relative error comes out to be this. Our propagated error comes out to be this. Okay, and that should be enough to allow you to do the problems for today. All right, hope you have a great day.